So in this video we're just going to look at some more results on primes, following on from the previous video where we looked at the methods for constructing a table of primes and simming out the composite numbers. We could extend these methods to arbitrarily large tables of integers, and if you do that you'll find that the number of primes less than 10 million is 664,579. So that's about 6 or 7%. Okay, if we look at a larger set, the number of primes less than a billion we find that there are 50,847,478, which this time is about 5%. So we see that the number of primes isn't really coming to an end. Of course we shouldn't expect it to, but it is showing a slow, steady decrease as we look at larger and larger sets of integers. So these results suggest Euclid's second theorem, which is theorem 4 in Hardy and Wright. The theorem says that there are infinitely many primes. I made a previous video explaining Euclid's theorem, that there are infinitely many primes, and proving it. We won't prove it in this video, I'll save that until chapter 2, but if you're desperate to see how this can be done, then you can look in the Hardy and Wright, or you can watch our other video. Let's now look at the average distribution of prime numbers, so to speak. So the sequence of primes is highly irregular, but it shows a great deal more regularity if we zoom out, so to speak, and look at the average distribution. So for example, the number of primes in the first block of 1,000 numbers. So between 1 and 1,000 we've got 168 primes, and in the second block of 1,000 we've got 135, 127, and then in the fourth we have 120, and the fifth 119, and I'll run out of space there. Nevertheless, you can see that there's this same steady but slow decrease as we move. Okay, moving on now to, so the next question I want to look at is how long can a chain of composite numbers be in the sequence of primes, i.e. is there any limit to the number of consecutive composite numbers we can see before we have to see another prime? If you look at the video on the sieve of Eratosthenes I made, you will see that the interval between each prime number isn't fixed clearly, but it doesn't vary greatly in the first 100 numbers. But theorem 5, which we'll get to in a second, deals with this question. So we want to suppose that 2, 3, 5 and so on up to some prime p. These are all the primes that are not greater than p. So every number between 1 and p will be divisible, well, excluding 1, every number up to p, and it doesn't have to be a prime number, will be divisible by one of these numbers. Therefore, if we multiply them all together, up to p, we'll create a number called a q. Then there will be p minus 1 numbers, which we can label q plus 3, q plus 4, q plus 5, all the way up to q plus p. So that is a set of p minus 1 numbers which all have to be composite. So that brings us to theorem 5, which says there are blocks of consecutive composite numbers whose length exceeds any given number again. In other words, there is no maximum length that a block of consecutive composite numbers may be. It can be arbitrarily long. So that's a result about how long how long a block of consecutive composite numbers can be. At the other end, well, the smallest length that a block of composite numbers can be is 1. So we never have two consecutive prime numbers, but we can have what we call twin primes, where p is a prime but p plus 2 is a prime. So these are called twin primes. So examples would be 3 and 5, or 101, 103. These are twin primes. What can we say about these numbers? So these patterns suggest a conjecture, or indeed a theorem. No one has been able to prove this theorem as yet, so it remains a conjecture, and it's became known as the twin prime conjecture, and it says that there are infinitely many twin primes. So this is still an area of active research. People trying to prove this for quite some time now, and efforts are ongoing, but there has been recent progress by people like Terence Tao, and who knows, maybe this one will be proven in the not too distant future, but for now it remains elusive. And of course Hardy and Wright don't prove it, we just state it as a conjecture. So yeah, we'll stop there for now with the twin primes stuff. So moving on, we will just briefly ask some questions about this sequence of prime numbers that might generate new insights. So first question we ask is there a simple general formula for the nth prime? In other words, is there some formula you could write down where you evaluate for a certain n and it gives you the nth prime number? All the evidence seems to suggest that this is not the case. No one has been able to find any such formula, and the sequence of primes seems to be complicated enough that it resists attempts to formalise the pattern. At least it has resisted anyone's attempts so far. So that's one thing we can say about the sequence. We also might look for a simple formula which would give us the next prime number given the previous one, some kind of recurrence relation, say, where we could evaluate the next prime number given the last one. We don't have such a formula, and the answer at the minute is no. Is there a rule where we could find not necessarily the next prime but just a greater prime? Given some prime, we could always find another prime which is bigger. Again, we don't have such a formula. We have some people who thought they had found such numbers. Fermat thought he had found Fermat numbers, Fermat numbers, which he believed to be all prime, but this was not the case. A better question to ask is how many primes are less than a given number. So this gets us to the prime counting function, which we usually label pi. So if I say pi of x, then this function pi of x is what we call an arithmetic function, which is one of the main objects of study in number theory, where we're going to look at functions which have integer values. They take integer values. So the prime counting function is a prime example, no pun intended. It just tells you the number of primes that are not greater than x. So pi of 1, 0, pi of 2, be 1, pi of 3, 2, pi of 20, be 8, and so on. And we can evaluate pi for any integer, and the output, or the result of the function, will always be an integer too, and that makes it an arithmetic function. Okay, so we'll stop there for now. The prime counting function is going to become very important in number theory, as I've suggested, but we'll leave it there until the next video.